Good morning, and I'm Dolphy Gilpin. I'm coming to you from the Springhill Marriott, Newark International Airport. That is Springhill Marriott, Newark International Airport. And this morning, I want to accomplish some electricity problems. We're going to solve some electronics problem using Kirchhoff voltage law, Kirchhoff current law, and Ohm's law. And later on, I want to introduce to you, as I always do, the amazing 5x12 matrix discovered that has been really stirring up the minds of students, scholars, scientists. It has a wide range of application, and we'll get to that a little later. But this morning, just some basic electronics problem using Kirchhoff voltage law and current law. Okay, so here we are, and suppose if we have no basic circuit. And I'm not going to use the numbers in this problem. I'm going to have to formulate the numbers on my own. Okay, so we have the basic circuit, and suppose now we call this now, say, VA, and suppose we call this a resistance R1, and say R2 and R3. Okay, this is positive and this is negative. This will be positive, negative, positive, negative, positive, and negative. Now, Kirchhoff voltage law, KVL, Kirchhoff voltage law, said now that the sum of the voltage around a closed loop, the sum of the voltage around a closed loop, and that is the summation sign, must be equal to 0. Another way of putting it is to be saying now that the sum of the voltage rise and the voltage rise in a circuit, which is usually equal to the source voltages, must be equal to the sum of the voltage drop, which is the voltage across the resistance. So if we say now the summation of the voltage, and we call it summation of V, must be equal now to VA, source voltage, minus now, this is a plus because we usually denote the source input voltage as a plus. The drops now will be R1, and suppose if we say now that this current flowing here is now I, so we know that by Ohm's law, the drop across here will be IR, so that will be equal now to minus I1 R1. We're going to call this I1. Although this is also one circuit here. So this is another V equal IR1, and this will be now minus because this is another drop. Yeah, this is another voltage drop, minus I1 R2, and this is another voltage drop here, minus I1 R3. And this must be equal to 0. So if we assign now a number here to this resistance, and the resistance is by definition equal to opposing the flow of the current, or resisting the flow of the current. Suppose if we see that this is now randomly, say 2, 3, and 4 for the resistances, and this will be in ohms now. then we say no that, and suppose if we assign a voltage of say 10 volts to this VA, so that what we have now, we have a known quantity here, known. So what is unknown here would be the current. So we say now that VA 10 minus now I1, and I1 is common throughout the circuit, I1 into R1 plus R2 plus R3. So we factor I1 now, must be equal to 0. And so we say now that 10 minus I1 into R1 is 2 ohms, plus R2 is 3 ohms, and plus R3, which is 4 ohms. And therefore 10 minus I1 times 9 is equal to 0, and therefore nine I1 is equal to 10, which give rise now to say I1 will be equals to 10 over 9, which is equal now to 1 and 1/9 power. Okay. So because of our random choice of the resistance, we know that the current comes out to be some 1 and 1/9 with some fraction. So this is using Kirchhoff voltage law and assigning some values for the resistance and values for the voltage, the source voltage. Or vice versa, we could assign a value for the resistance a value for the current and find the voltage. Now the voltage drop across each resistance here would be, if we call this say V1, and this V2, and this V3, you would say now that the voltage drop across this resistance would be I1 R1, and since we have found I1 to be 1 and 1/9, so the voltage drop across here would be now 10 over 9. V1 would be equals to 10 over 9, which is I1 R1, which is 2, would be equals now to 20 over 9 volts. Likewise, V2, the voltage drop across R2, V2 would be equals to the same I1, which is 10 over 9, times R2, which is 3. That would be equal to 30 over 9 volts. And now V3 will be equals to I1 10 over 9 multiplied by now the voltage, the resistance, which will be equals to 40 over 9. Note that if we add now, we said now that the sum of the voltage must be equal to 0. So if we add I1, R1, I2, R2, and I3, R3, and VA, that's supposed to give us 0 by Kirchhoff voltage law. So we have found V1 to be 20 over 9, V2 to be equals to 30 over 9, V3. So the sum of these three voltage, V1, V2, and V3 is how much? But these are drops, so they're going to be negative. So we say, no, this will be, some of them will be 20 and 30 and 40, 70, 90 over 9, which is equal to 10. Right? So the sum of the voltage drop, sum of voltage drop, I'm going to use the symbol here for voltage drop, VD. Sum of voltage drop is equal to 90 volts, and the sum of the source or the rise voltage, V rise, is equal to 10, which prove Kirchhoff voltage law. In other words, if we say now that the summation of all the voltage now, the rise and the drops, must be equal to 0. So what we'll have now that VA is 10 now, summation of V is equal to 10, which is VA, minus 20 over 9, minus 30 over 9, minus 40 over 9, which is equal to 10 minus 90 over 9, which is equal now to 10 minus 10 equal 0, which is Kirchhoff voltage law. All right, let's move on now to Kirchhoff current law. And to do this now, we're going to take a break. And we're going to come back to Kirchhoff voltage current law, which states that the sum of the current at a node must be equal to 0. Otherwise, the sum of the currents entering and leaving a node, sum of the current entering the node must be equal to the sum of current leaving a node. Or another way of putting it is that the sum of the current at a node is equal to 0. Well, we'll take a short break and then we'll come up to Kirchhoff